So let's start the class number 6 today on the 27th of January 2020. Refer back from the last class. We talked about the local coordinates formulations. So we use the local shape functions instead of the global one constructed in the physical domain. So we found that the physical domain construction is rigorous. You have to repeat your operation many times. As the element change the coordinates, you need to reconstruct the shape functions. That's the problem. That's the ineffectiveness we had in that scheme. So the local coordinates and local shape functions were introduced in the last class, and then we formulate our weak formulations based on that local coordinates, and we conduct the integration. We get everything exactly the same as the global coordinate construction. The thing is that we can even we can improve the procedures in an even more efficient way, because the integration we deal with nowadays by the direct integration. So you carry out the integration in the same way you learned in the calculus classes. The thing is that the integration is not friendly for the computer programming. So if you want to construct, you can do this in MathCAD, you can do this in MATLAB, but the integration procedures just takes too much time, very time consuming, and that's going to slow down your computational procedures. So we will look into the better way to integrate your functions in your weak formulation. So the point is that right now the formulation we see over here, mostly we have the polynomials in our formulation. So we basically just integrate the polynomials. Alright? Okay. So we will talk about numerical integration. We call it Gauss Quadrature rule. And you will hear the word Gauss points later, okay, in this class. So numerical integration will eliminate our pain in doing this. You integrate the function from -1 to 1. Okay, the function f of c dc. So this is inconvenient. And slow. We will carry out these procedures. Instead of integration, we're gonna do the summation. So we're gonna sum the function f of c, which is the ci, and then multiply by wi, where I is equals to 1 to n. The n here represent the number of Gauss points you use in your integration scheme. Number of Gauss points is to be determined So for polynomials, for f of c be the polynomials with the sufficient number of Gauss points, the integration dc can be evaluated explicitly. That means you can get the 100% exact solution. So let's take a look. We express f of x in terms of all polynomials. So we have the a0. A stands for the constant coefficients. a1, c linear term, a2, c square, a3, c cube, and so on, so forth. So essentially, the beauty of this approach is that you will not transform this function into like a0 c plus a1 c square over 2 plus etc. You don't have to do this. So you will just evaluate the function using the given ci and wi. Okay? Just that. So life will be easy because the functions over here, you might not even have to make it to this form. Sometimes you have like 3 minus c square and then 5 over 2 plus c multiplied by 1.0 plus c cube. You don't need to expand these terms into the a0 plus a1c plus, you don't really have to, because if you know that this is f of c, you just substitute c1, c2 into this c. Then you can evaluate the function value. You don't need to expand it. You evaluate the numbers. That is easy. You drop it in, the computer loves this, right? And then once you get the f at ci, you multiply by wi. The w is the weight of each integration point. So what are to be determined here? The first, the ci, the second, the wi. That's it. So ci and wi are to be determined. So let's take a look. First case, if f of c is a linear function, so f c is equal to a plus a1c. That's it. So you put this in minus 1 to 1, and this thing in here we paste there, and dc, what you get here is okay, we say that it is equals to summation so we have the w1 and a naught plus a1 c1 plus w2 a naught plus a1 c2 plus w3 a plus a1 c3 no, plus w4 a naught a1 c4 plus alright, because right now you have no idea how many integration points do we have. So on the left side you can carry this out. You have a naught c, right? A naught c, so that is, oops, sorry, that turns out to be a naught times 2 plus a1 times 0, because you have the odd power of your polynomial c. We know that it's gonna be 0. And then we can group up the terms on the right hand side. So you have a naught times w1 plus w2 plus w3 plus w4 oh sorry, the c, oh okay, yeah, that's correct. And then plus a1 times, what do we have for a1? a1 times c1 w1 plus c2 w2 plus c3 w3 plus c4 w4 plus, so we have this form. So from here we can break this down into two equations. First equation there, second equation here. The thing is that you're gonna equate the terms, the coefficient terms that scale the A0 and A1. So let's write that down. We're gonna end up with two equations. The first equation, 2 is equals to W1 plus W2 plus W3 plus, and the second equation, 0 is equals to C1 W1 plus C2 W2 plus C3 W3 plus. So right now, let me ask you, what is the maximum possible number of I value that we can figure out from this given condition? The I is the number of integration point. If you have one integration point, if it is 1, you're gonna have two unknowns, C1 and W1. Once you have 2 points, you're gonna have C1 W1 C2 W2. That's gonna break you down into 4 unknowns. So to solve the equation, right now the equation is not that well, later on you find that it might not be just the linear equation, but you will need at least 2 equations to solve 2 linear equations. Alright, so for now, in total you have 2 equations. You cannot have more than 1 integration point. You cannot have more than that, because you will not have enough equation to solve and to determine this out. And that's why this is not possible for a higher term. Likewise, so we find that the weight is equals to 2 and the C is equals to 0. The graphical meaning of this is quite easy to illustrate. This is your function value in y-axis. So we have Right. This is your function f of c that is equal to what is this point of intercept? This is actually equals to A0. As your C value is equal to 0, your function is going to exhibit the value of A naught, right? So you want to integrate. If you want to do so, the area will be the result from your integration. This in here is equals to -1 to 1 f or the a naught plus a1 c dc, the area. So to calculate the area explicitly, you take the height, this height, and then add them up, right? Multiply by a half, multiply by the base, which is equals to 2, you get the area. That's the explicit where you integrate the function, whereas the numerical integration offers you something which is quite effective, because from numerical integration, the integration from -1 to 1, I put it this way then, the summation from I equals to 1 to 1, because this is just one point, f of c, and your c is equals to 0, multiply by the weight, which is equals to 2, that is a0 plus 0, a1 multiplied by 2, which is equals to 2a naught. Basically, this is associated with this. So 2 times a naught. 2 is from this, right? The base being 2, the height is a naught. So this rectangular shape is actually equivalent to the trapezoidal shape. Over here, you integrate, you get a naught c, evaluate from -1 to 1, you get 2a naught. Or if you want to calculate the area, then you get the height here, a naught minus a1, and this is a naught plus a1, so you take these two adds up, you get 2a naught, multiply by a half, multiply by 2 as a base, then you get 2a naught. Okay, so just showed you that it works. So it is much faster than carrying out the integration. But we will not just stop at just linear function, because most of the time we be dealing with the higher order polynomials in the finite element calculation. So let's take a look at the other higher order polynomials. So we integrate from -1 to 1. Well, first of all, let us think before we do anything. we can have one-point integration. One-point integration offer you the possibility to integrate the linear function. The linear function contains two terms, the terms a0 and terms a1. Okay, so we take the coefficient, the part that multiply to a0 equate to the other side, the part that multiply to a1 equate to the other side. You end up with two equations. These two equations are used to determine two unknowns from your Gauss point. One Gauss point gives you two unknowns. Alright? That means when we move to the next step, you are going to have two Gauss points. You cannot have 1.5 Gauss point. Alright? The point is the integer. So you have two Gauss points. That means you're going to end up with four unknowns, two C value and two weights values. Four unknowns. That means you need four equations to determine four unknowns. And in order to get four equations, you need A0, A1, A2, A3. Or, in other words, you are capable to evaluate the polynomial of which the highest function, highest order of the polynomial is the cubic. Right? We have A0, A1, A2, A3. A0 is associated to just the constant. Right? So, we are going to do the cubic polynomials for this next case. So you have question in your mind, what if I have the quadratic polynomial? What could I use? The quadratic polynomials is actually the subset of the cubic polynomials. You just have A3 being 0. Right? The coefficient that scale the C cube is 0. And that's why the quadratic polynomial can be evaluated using two Gauss points, which is under the same umbrella as the cubic polynomials. In fact, just order 1 or just the linear term like before, linear function can be evaluated using two integration points technique as well. So that is the case where you have A2 and A3. Both of them are equal to 0. So linear function can be evaluated using two Gauss points, 3 Gauss points, 4 Gauss points, etc. Gauss points. The thing is that why should we overuse our resource? If you can achieve the exact number, right? If you can get the exact solution of the integration using just one, why should you use two to evaluate? Because that is going to add you more computational cost. That's just it. So that's why we look into this. We don't just go all the way to 10 integration points, because it just wastes your time. One integration point is going to make one loop operation. You're gonna evaluate stiffness, you're gonna evaluate the whole matrix, many things at one Gauss point. So the more Gauss point you have, the slower the operation will be from your code, right? So we will check it out explicitly. We will see the possibility what might be the highest order of the function inside your integral. Knowing that, you determine the number of Gauss points corresponding to that order, and that will be the cheapest cost for your calculation, that you still get the exact solution. Well, later on, when we talk about the Timoshenko beam, we talk about the shear stiffness, and when we talk about quadrilateral element and shear stiffness, you'll be hearing the word reduced integration. I'm gonna emphasize that again. If you might not need to write this down right now, because it's gonna be a big issue to talk. So reduced integration is the way that you have, for example, you have the cubic polynomials, and then you evaluate that cubic polynomials using just one Gauss point. Can it be done? Yes, but the accuracy will drop. That's the problem. So you can do it. You can use the reduced number of integration point. You don't fully satisfy the requirement in order to achieve the highest level of accuracy, zero error. So you reduce number of integration point, but still, but you will, you will get rid of some issue, some problem from having the full integration. Okay, so that will be later, right? But it can be done. So right now, our function is a0 plus a1 c plus a2 c square plus a3 c cube dc. That is equal to, on the right hand side, you have a0 multiplied by w1 plus w2 actually I may not really have to write this to w3, w4, because you'll be able to accommodate only 2 points, so w3 will be just not included in here, plus a1 c1 square, c1 w1 plus c2 w2 plus a2 c square and then a3 Q Q Q and that's gonna make a0 w1 plus w2 plus a1 c1 w1 plus c2 w2 plus a2. Okay, So on the left hand side you have what? 2 a naught plus again 0 a1 plus 2/3, right? Square turns out to be cube. Okay, 2/3 a2 plus 0 a3. I'll be taking out this so equate this up. 2 equals to this one. 0 is equals to this term. Another 0 for this. Oh, sorry, not 0, 2/3. And 0 equals to the last one. If you do a little cheating, saying that W1 and W2 okay was supposed to be symmetric, then we're gonna solve all of this out very quickly, right? First of all, you can figure out that the function, the equation we deal with, these are not the linear equations. You have the square term, you have the cube term, they are not the linear equations. If you have the linear equations, then you'll be able to calculate everything, determining the values of unknowns using just 4 equations. But now equations turns out to be nonlinear equations, so you might need to use some extra condition, extra equations in order to solve all of this. So when the W1 is well, first of all, C1 is equals to minus C2. Okay, we give this as an extra condition. First one, we're not going to do anything. For the second one, if C1 is equal to C2, C1 W1 minus C1 W2 equals to 0. So that means W1 is equals to W2. Okay, as W1 is equals to W2, so this is substituted by W1. We end up with the W1 equals to W2 equals to 1. Over here, C1 square times 1 plus C2 square, which is equals to C1 square times 1 equals to 2/3. So your C1 square is equals to 1/3 C1 is equals to square root 1 over square root of 3, and your C2 is equals to minus this value. Put them together. You can try. Just name some function. Let's do integration minus 1 to 1 of 2 plus C minus a half of C cubed BC is equal to, oh, it's too bad, this dissolve, right, because they are the odd term polynomial. So this one turns out to be 4. Not fun. Add something for the square term. You can have the missing square term like this, alright? So that means that A2 is equal to 0. Just that. You might not have a complete polynomials. You might not have all orders polynomial below 3. You can miss the linear term, constant term, quadratic term. You can have just C cubed only. That's fine. Okay. Gone. So we have 2 multiplied by 2 minus 5 multiplied by 2/3, right? C cubed, okay, over 3, so 2/3 is it equal to 2 to 4, 4, 12 minus 10, so ends up with 2/3, right? That is the exact integration. Now we carry out the numerical integration. So you have f which is evaluated at multiply by weight, which is equals to 1 minus, add up with 2 we need to correct something like this. So this term cancel out, this term cancel out, you end up with 4 minus 10 over 3, just like above, 2/3. Keep in mind that the Gauss point we have over here is for the domain of integration from -1 to 1. This is not generalized case, right? If you want to get the other case mapped onto this one, then you're gonna conduct some sort of mapping. For example, if you want to integrate the function of x from 0 to 5, then you have to do the mapping. So the -1c is mapped to the x equals to 0, and x equal to 5 map onto c equals to 1, something like that, and then you will have the scaling factor and so on and so forth to adjust, because this is suitable for this numerical domain, okay, from -1 to 1. You can come up with the c and weight value if you have the different domain of integration. That is possible, but you need to recalculate all the things. You recalculate the c and the weight corresponding. Okay, so the next step, above these 2 integration points, then you're gonna bump into 3 integration points. Generally, the standard FEM, we use the quadratic interpolation function as the highest polynomial, since it can capture the curve, and we're happy with that. So we have quadratic polynomials. We will have the du dx, so we're gonna have the polynomials drop down by 1 order, but then it's gonna multiply by another du dx. Alright. So basically, the order of the polynomial inside the integral is not like to the extremely high order, right? So 3 points generally suffice for finite element calculation. So 3 points. Let me ask you, what is the highest order of polynomial that will be exactly evaluated by 3 points integration? you have how many unknowns? 6 unknowns from 3 points. So you have A0 all the way to A subscript 5. The maximum order of polynomial is to the power of 5, right? Higher than that, it will be just an approximation. It will not be exact. So you can do all of this. I'll be picking up the number from number I had before. So first point, C1 equals. Second point, and the third point. I'm bringing the number I had before, okay, which is quite long. Okay, I just copy the whole thing there. The thing is that this is what we generally do for the finite element business. The coefficients like this, 1 over square root of 3, if you leave it this way when you code the program, when you write the code, you say that C1 is equal to 1 over square root of 3. The issue is that you're gonna deal with this number for seriously so many times. So many times, it's like million times. So if the computer evaluate 1 divided by square root of 3, square root of 3 takes time for computer already. Well, it is a fragment of a second. Still, it takes some fragment of a second. Once you multiply this fragment of a second to like million, trillion operation, that's a lot. Because when you evaluate just one integration point, you deal with this 1 over square root of 3 many times. So to avoid that, then you substitute the 1 over square root of 3 by the number. But you just need to maintain the accuracy of this number. So you're gonna maintain like for this generally 15 digits of decimal place. You keep it. So you write it down. You hit the calculator. You get 1 over square root of 3. Quite long. Then you take the first 15 digits and put it there in the computer. You truncate the latter digits because it's not going to affect your accuracy significantly. Well, we keep that many, right? So don't put this in. Into your code. This got to be what, 8 over 9, 5 over 9, 8 over 9. I'm not exactly sure about this number. The square root of something over I will see if I can keep it there. Okay, 1 over square root of 3. You have it here. Don't worry, you're gonna get the video of this thing, so you can look up. Actually, your calculator can do it, so don't worry. But I don't remember C1, C2, C3 from what square root over something. Okay. So you can try to evaluate the function using these 3 Gauss points as well. I'm not going to do it here. Okay, so you can use this to evaluate your weak formulation. Okay. I shall request you to do some sort of homework as the last piece of the bar element before we move forward to the beam element. So for the bar element, it's time to code. So this problem here, I think, is gonna force you to code up. I'd like you to do the quadratic interpolation functions. So you'll be having the middle node. So the nodes are given. Make it L. well, we can just call it super assignment. So you get more points than normal assignment, as it is. It shows the sense of super. Super assignment. Okay, 9 elements. So you start from the U0, U1, U2, so on and so forth. We have some special thing. So the cross section is EA in this zone, and EA varies linearly from here, which is EA, to 3EA. So you can write the function of EA right. It is a function of x. Well, later on you can convert from x to c. It's not a big deal. So make that function for your own. And the load should be this is a bar problem that the computer method techniques you learn might not be capable of solving. F function of c is equal to f times, oh sorry, function of x, not c. Zero point 3 x over 1, 2, 3, 4, well, over 9L plus 0.4 x over 9L square that means inside this is to be converted into f of c, but that is for individual element. Because your x and your c, for each element, these relationships are different from the different way you map. The xi will keep changing. Okay, right? So inside, let's see what we have. We have the EA, and that is the constant of EA taken out, multiplied by the function of x, that is for EA. Right. And then you have the du dx, dw dx, dx. Essentially, the whole thing, after you change from x to c, that's gonna be like a big piece of equation. So you're just looking into it. What is the order here? What is the order there and there? You see the maximum order of your polynomial in this group, and then you select the right Gauss number of Gauss points you need to evaluate this explicitly. Alright? And then just evaluate this circle. You don't really have to perform any integration from here. Life is so beautiful. So over here, the computer, the algorithm from your computer, basically you might not need the computer. Okay, you can do this by your Excel can handle this. It does not need to be MATLAB. If you want to use MATLAB or Octave, okay, it's your choice, right? Doesn't I'm okay with all. But my point is that right now everything is friendly to the computer operation. So you evaluate the functions like this. You just drop in the functions, and then you substitute the c value, and that's it. You summation, you get the function value very easily. Right? You just think of the algorithm that bring you there. On 9 elements, if you still want to do the hand calculation, it's fine. It just takes some time, but it's just fine. So you have how many? You have 19 degree of freedoms in here. You still can handle. You have 19 equations to work on. Just that. But you copy and repeat things. Right? If you set up the whole line of equation and changing just some coefficients in Excel, you make tables and then you have coefficient A, B, C, D, E, F from one equation. You can make like a closed form of the equation. That could be also done, right? And then plot out the displacement solution, stress distribution. You have today is Monday, so you have the Thursday of the next week. Fair enough. It might be quite a long calculation, so you might need some time to think of how to do it, okay, for a few days, and then once you bump up with the procedures and you continue there. But the fundamental understanding, mutual understanding we have for this course is that you're going to do it for yourself. As I give you more time to trial and error, okay, go through this learning process. You gotta do it for yourself. It is still bearable, it's still not too difficult to do, but you just need to work on it, think and spend time and do it. Alright, so the due date is so I add up with 7, then it is 31st, 1, 2, 3 is Monday, 4, 5, 6, right? 6th of February. That's a due date. So do it for yourself, or you're gonna do it in the exam. I can make the problem like this very easily for the exam. It's gonna take you like many hours, so I can beat the record, 6 hours for earthquake. Okay, I can make 12 because one problem is gonna take you like a few hours. I give you 5 problems, then you sit there from the morning to the evening and just have a good time with finite element that you will not like to end up with that, right? So maintain your dishonor system, right? Do it yourself until the last homework. Yeah. That means you have the class on Thursday this week and Monday in the next week to come in and to talk. So if you want to ask anything, ask in public. Do not ask behind the class, after the class, behind the scene, alright? Because the information will be shared throughout the class. That is the most effective way. I do not need to repeat anything if more than one people wants to ask the same question. So work on it to some extent. Okay, come to the next class. I give you time to talk and ask about this. Okay, you get through that point. Over weekend you do more. On Monday, maybe you are like 60-70%, come in and ask for more, and then you wrap up over like a few days after Monday. So this is fair enough for you to have opportunities to ask and whatsoever. But I do not guarantee one thing, that the next class I might have smaller assignment, right? So it is not like you are proven from any assignment over these 2 weeks, because it might come overlapping on top, but it will be the smaller one on top if you have. Okay, so just that, nothing quite special. Right, now I move over to the flexures. So the beam element they are totally different. The formulation will tells you how they are different from each other. Quite different, totally idea. Euler beams, no shear deformation. So you can guess that another one incorporates the shear deformation. So this one is suitable for deep beam. Different sets of shape function will be used for these two different elements. So we start with the Euler's beam. For Euler's beam, actually we come across this element in computer method already. So one element you have two nodes. You don't want to put the node in the middle because you'll be dealing with higher and higher order functions. The more control points you have, the higher order functions you're gonna get, right? Too messy. Right? It is not a standard one. If you want better solution, then discretize more. That's it. You don't go that direction. Just discretize more. So you have unknowns. This will handle the four degree of freedom. In order to control the polynomials using four constants, what is the highest order of polynomials that we can use here? You have two control points. Each point has 2 degree of freedoms, right? So you have 4 degree of freedom. 4 degree of freedom, you're gonna get 4 shape functions. So there will be shape functions for each mode controlled by each degree of freedom. But let me ask you, okay, for each shape function, what is the highest order of polynomials? I mean, for the beam, for this beam element, what is the highest order of polynomial we can handle? So it should be the polynomials that contain 4 variables, not 4 variables, 4 constant coefficients, right? So f of c, which is the shape functions of the polynomials that is associated to each of the points. You have a0 plus a1 c plus a2 c squared plus a3 c cubed. This is the highest polynomials, highest order of polynomials that we can come up with to use for this given beam element, 2 nodes, 4 degree of freedom. Why? Because first of all, if you want to have the polynomials for u1, a shape function for u1, what is the requirement for the shape function for u1? The shape function here, I will just change from x to c. The shape function here must exhibit the displacement equals to 1 when c equals to -1, right? And then decrease down to 0. It shall not exhibit any rotation. Rotation has to be 0. At this point, 0 displacement and 0 rotation. So basically, to come up with one shape function, you have 4 boundary conditions which are from these 4 degree of freedom. And that's why you can just get the cubic interpolation function. You cannot go beyond that. You don't have more degree of freedom that will control your shape function. Alright, that's just it. So, first of all, phi at minus 1 is equals to 1. Phi prime at minus 1, phi prime, to make it clear, we have the dc, d phi dc evaluated at minus 1 equals to 0 because we do not expect rotation. And phi 1 is equals to 0. And 1 equals to 0. So these 4 constitute the boundary condition for us. Sorry. One at a time is equals to 1, and that is that is equals to a naught plus a1 times minus 1 plus a2 times minus 1 square plus a3 minus 1 cube. And next one, 0 is equals to 0 times a0 because you differentiate, right? a1 times 1 plus a2 times 2 times minus 1 plus a3 times 3 times minus 1 square. Right, you just differentiate this shape function with respect to c, and next you substitute the c value being equals to minus 1. So I will copy this and paste. So this is minus 1 okay, that's just it. Now convert this into the matrix form. So 1 minus 1 1 minus 1 0, 1, minus 2, and 3. 1, 1, 1, and 1. 0, 1, 2, and 3. You have A0, A1, A2, A3. So you will end up with the derivative of the first shape function. You can determine the constants A0, 1, 2, 3 for the shape functions, and you will get the following. Use Microsoft Excel. I don't show it up on the display. I don't want to switch around. Basically, one minus 1, 1 minus 1, 0, 1 minus 2, 3, 1, 1, 1, 1, 0, 1, 2, 3. Right, so you just inverse in order to get this solution. MULT of M inverse, matrix inverse of that. Right, so we have 0.5 as a A0 minus 0.75 as the A1, 0 for C square, and plus 0.25 for C cube. So you can plot this. You will end up with minus 1 to 1, the shape like this. 0 slope, 0 slope, 0 value there equals to 1 over here. Okay, check, yeah, plot it. And then you just repeat the same thing. This whole thing, you just change the boundary condition. Just that. You copy the whole thing down. The only thing you change so the shape function for the second that is associated with the second degree, the degree of freedom number 2 at the left node, which is the rotation, right? You just need the rotation to be equal to 1, and then other degree of freedom should exhibit 0 value. So this is it. But the evaluations is still the same, right? You just need to determine A0 to A3. If you substitute the value of C being -1 and 1 at each point, okay, this is what you get. So I can just continue 1 and 0. This is what I get here in prelim equals to 0.25 multiplied by 1 minus C minus C square plus C cube just like this. My point is that right now we have this relationship holds for the domain where C equals to -1 and 1. In reality, your physical domain will be the different size. I mean, the length is equal to 2 for here, whereas for here the size is equal to L. So you have some height this is determined by the phi. So the peak point, let's call phi max. Okay. My point is that when you construct the shape function in the local coordinate and then you map it onto the physical domain, for the shape function associated with the displacement degree of freedom, it doesn't bother, it doesn't make any problem. Okay, so it gets stretched let me just show it this way. The other thing, copy and paste. The other type, delete. Okay. Now you're gonna see. So the one that we talked already, it's gonna look like this, right? For phi 1. So when you stretch it out, it is just goes like this. Okay. So the phi max and phi max match, and if you need 1, you're gonna get 1, right? This doesn't bother when you map from numerical to the physical domain. It does not cause any problem. But for this one here, we have the shape function that control the rotation, which is equals to 1 in the numerical domain. You expect the rotation to be 1 in the physical domain, right? That's a real place where the physics happen. The thing is that once you map this shape function onto the physical domain, you get the ratio of 1 divided by L over 2, because you have the stretching in just one direction. So you were supposed to have the slope equals to 1, but then you stretch the x-axis, your slope is changed, right? You don't get the one you want. You suddenly just stretch one axis. So in order to maintain slope, then you need to also scale this up from the red line here to the blue line there. You scale it up. Now you can see that you end up with 1 over L over 2. That is the stretching factor you had when you map from numerical to the physical. The physical domain length is L, numerical one is 2. So stretching factor is L over 2. So you stretch just x-axis, then you have the slope is dy dx, right? So dy dx, but you scale the x up, right, by L over 2. Then your slope turns out to be not 1, but 1 divided by L over 2. So to correct that, you scale the y-axis or the shape function axis up by L over 2 as well. That is going to put everything back into this one. Slope will be equals to 1, like our intention. So this is not the finished product of the shape function number 2 for the slope. For the rotation at the left node, you multiply by h over 2 or L over 2. Let's call it h over 2. H is the element size. So little homework that is due on Thursday. I need you to plot phi 1, phi 2, phi 3, phi 4. All of these phi 2 and phi 4 give me the one which is not scaled by h over 2. So you have the -1 to 1, everything not scaled by h over 2. Right? Let's just do it this way. I calculate you phi 1, phi 2 already, so you need to calculate phi 3 and phi 4, right? And plot all of them in the same plot. Just that. It will be short one. Right. So this is the extent of your x domain from -1 to 1. Alright, that's it for today class. We're gonna see you again on Thursday.